Good afternoon, everyone. Sometime in 1996, a fighter plane crashed due to a fault in the compressor of one of the engines. The in-situ investigations found that the central bearing of the compressor shaft had failed before its specified lifetime. And the failure analysis showed that the cage of the bearing failed due to fatigue. A broken piece from the cage got stuck between the bearing bolts and the races, what made the shaft rotation difficult and led to the crash. Of course, early bearing fault detection and surveillance could help prevent such catastrophic disasters. I'm Mohammed Albezzawy, a master student and a teaching assistant at Albezzawy University, Egypt, and I'm going to introduce a technique for early rolling bearing fault detection using a Gini index guided adaptive Morley wavelet filter. In the following slides, after giving a brief introduction, I'll state the problem definition and the objective of the work, and then I'll explain the methodology and the algorithm, the adapted algorithm. After that, I'll show the algorithm verification and validation. Later on, the results will be displayed and discussed, and finally, I'll state some conclusion and some ideas for future work. Rolling element bearings play a fundamental role in many critical applications, such as aerospace, automotive, and energy systems. Early bearing fault detection could help not only prevent catastrophic failures, but also reduce maintenance and downtime costs. Bearing faults usually start as a local fault. During shaft rotation, every time this fault strikes the mating surface, an impact is produced, which appears in the vibration signal as an impulse. As the rotation continues, an impulse train is produced in the time domain of the vibration signal, which is the characteristic shape of incipient bearing faults or small bearing faults. The reciprocal of the time interval between two consecutive impulses is called the bearing characteristic frequency. The bearing characteristic frequency can be calculated from the bearing geometry, which is known. And any bearing has 4 bearing characteristic frequencies, whose values depend on the location of the fault. A fault on the outer race produces a bearing characteristic frequency called the ball bus frequency of the outer race. And if the fault was on the inner race, so we got the ball bus frequency of the inner race. Whereas the cage fault is called the fundamental train fault, or produces a frequency called the fundamental train frequency, and ball faults produce the ball spin frequency. Okay, 4 distinctive values. So we can detect a fault and identify its location just by detecting one of these frequencies in the vibration signal. The problem is that the signal that we've seen previously wasn't a raw signal. It was a processed version after processing with my methodology. Okay? The raw signal looks like this in the figure, where no repetitive impulses can be seen, so no bearing faults can be diagnosed. And this is due to the fact that small faults signals are usually masked with heavy noise and vibration signals from other sources. And this is quite often in complex systems like helicopter gearboxes. Envelope analysis is a signal processing technique which is typically used to solve this problem. Envelope analysis enhances the impulsive feature in the signal by a process called demodulation. Based on the fact that the demodulation is based on the fact that the faulty bearing signals modulate the bearing system resonance. Okay? However, its success is conditioned by selecting the proper frequency band for demodulation. This is the raw signal in the frequency domain. The useful information about the bearing fault is only in the resonance region here. So we have to band pass filter around the resonant frequency. Okay? So the objective of the work is to early detect small faults through denoising the vibration signal to enhance the impulsive feature. And this is achieved by proper filtration. Based on the objective, so the developed methodology was the design of an automatic and adaptive band pass filter. And adaptive means that the filter can adapt to any input signal. That filter can blindly select the proper pass band for demodulation. And blindly means without prior knowledge of the system's resonant frequency. The developed algorithms consists of three main components. The first component is the complex Morlet wavelet, which is used here as the band pass filter. And we chose it because it has a shape similar to the shape of the vibration produced by a mechanical impact, okay, in the time domain. The second component is Gini index. And Gini index is a statistical sparsity measure, which is originally used by economists to analyze wealth distribution. Gini index is used here as the filter selection criterion because impulsive signals are sparser than noisy ones. So he can select. And the third component is a specially built heuristic inspired by particle swarm optimization with some modifications. And is specially built to optimum filter selection. The algorithm starts with feeding the raw vibration signal, along with some information about it, like the sampling frequency, the rotational speed of the shaft, the bearing characteristic frequency of the bearing. And this is the wavelet that we want to optimize. These two things are fed to the particle swarm optimization algorithm, or the heuristic, the built heuristic. And the fitness function is to maximize the Gini index of the filtered signal, or namely the Gini index of the squared envelope of the filtered signal. Okay. The output of the optimization process is the optimum filter, which is a filter that produces a filtered signal with maximum Gini index, or in other words, maximum impulsiveness. This is the filtered signal, and this is the raw one, using an optimal filter based on Gini index. And finally, to diagnose the fault and know its location easily, we transfer it from the time domain to the frequency domain, and we determine the envelope of it in the frequency domain. And we will see the benefits of that in upcoming slides. We did verification and validation for the algorithm. For verification, we generated an inner race fault, which is designated as signal A. And then we added white Gaussian noise to it. So its signal to noise ratio decreased to minus 15 decibels, which is considered very low. After that, we feed this noisy signal to the designed filter. And we get a filtered signal with enhanced impulsiveness. Okay? It's clear here. It is the raw signal, and this is the filtered signal using the designed filter. Okay? And this is the squared envelope spectrum. For envelope analysis, we have to determine the squared envelope spectrum. Okay? And in the squared envelope spectrum, it is seen that we have a large amplitude, a high amplitude at the rotational speed of the shaft, which is a characteristic for inner race fault signals. And we also have a dominant amplitude at the bearing characteristic frequency, which was the ball pass frequency of the inner race. What identified the location of the fault. The fault is in the inner race. And also we have side bands with the rotational speed, which also are characteristic for inner race fault signals. And the squared envelope spectrum showed up to the 9th harmonic of the bearing characteristic frequency, which shows that the Gini index and the proposed methodology is so powerful. Because as many harmonics as you see, that proves the strength of the algorithm, because many harmonics ensures a faulty bearing case. For validation, we use two experimental signals, which are designated as signals B and C. Okay? I think I took them from the Case Western Reserve University bearing data center. The test rig consists of an electric motor driving a shaft in which a torque transducer is mounted. Okay? And they change the torque by this motor. And faults with different sizes were introduced separately to the test bearings. They have test bearings, and every test bearing have an individual fault. And vibration data were collected. The two used signals are inner race fault signals. The two signals are inner race fault signals. And the table here shows the signals information. It can be seen that the two signals are of two different sets of conditions. Signal B has a higher motor load and relatively larger fault size, which will result in the signal in a significant fault feature. The impulses will be clear. Okay? Whereas signal C has a zero motor load. The motor load is low, very low, zero. And the fault size is smaller, what will result in a weak fault feature in the signal. What means that the diagnosis of signal C will be harder than signal B. A comparative study was made with the results of a previous study which had applied a similar approach to the same two signals. They used a sparsity measure called the improved correlated kurtosis as the filter selection criteria. I used Gini index. Okay? And they found that the improved correlated kurtosis outperformed other sparsity measures, namely kurtosis and spectral kurtosis. They are all a famous measure of sparsity when used as criteria for optimum Morley turbulent selection. Okay? For comparison purposes, the results of the previous study will be on the left-hand side of the slide, whereas the results of my proposed method will be on the right-hand side. Okay? The squared envelope spectrum obtained based on the improved correlated kurtosis showed up to the third harmonic of the bearing characteristic frequency. Okay? When the results based in kurtosis showed up to the second harmonic only. And the results based on spectral kurtosis showed only the first harmonic of the bearing characteristic frequency. Whereas the results based on my filter, which is based on Gini index, revealed up to the fourth harmonic of the bearing characteristic frequency. Okay? Which proves that Gini index is more powerful than the previously used criteria. The results of processing signal C, which has a weaker fault feature according to its conditions. The results of the previous study, the squared envelope spectrum obtained based on the improved correlated kurtosis showed up to the second harmonic of the bearing characteristic frequency, when kurtosis showed only the first harmonic, and the spectral kurtosis failed to show any amplitude at the bearing characteristic frequency. Whereas, on the other side, the results based on my method, which is based on Gini index, revealed again up to the fourth harmonic of the bearing characteristic frequency. Okay, regardless the signal is very noisy or not. Okay. And you should know before I turn that it's known in bearing diagnostics, it's proper to detect at least up to the third harmonic of the bearing characteristic frequency in the envelope spectrum. It is a known rule, okay, in bearing diagnostics. So I have up to the fourth harmonic. Okay. Conclusions. A suitable optimization criterion is crucial in bearing fault diagnostics. The proposed adaptive Morley turbulent filter proved to be effective and efficient in detecting early bearing faults. And Gini index was found more accurate and powerful than currently used indices such as spectral kurtosis and improved kurtosis and kurtosis when used as criteria for bearing fault detection. Some potential ideas for future work. Maybe studying the proposed approach on more complex signals, and maybe combining Gini index with other filtration techniques other than the molecular filter section. Okay? Thank you. Any questions?